Welcome to the first annual Cosmos Lecture in Human-Centered AI. I'm Philipp Koralus, the McCord Professor of Philosophy and AI and the Director of the Laboratory for Human-Centered AI, or HiLab, that will open in the Institute for Ethics and AI this fall. It is my great pleasure to introduce our speaker, Professor Leslie Valiant of Harvard University and recipient of the Turing Award. Like Alan Turing, Les has driven mathematical insights into the nature of computation so far that they have become philosophy. Many eminent scientists try their hand at this sort of thing and fail. Les does something that is sorely needed. He applies his incredible mathematical mind to questions of the deepest significance that philosophers have tended to neglect. In this case, the question of the nature of human intelligence. In the age of AI, this question is now of the deepest practical significance as well. Like Les, I believe that making sense of human intelligence will also be key in further developing AI, particularly if we wish for AI to be human-centered. Les's lecture and his recent book, on display over here, focus on an aspect of intelligence that is without a doubt particularly key: educability. I hope I speak for everyone who is here today if I promise that we will do our part and exhibit educability in spades as we listen to his lecture. The Cosmos Lecture is sponsored by St. Catherine's College and the Cosmos Institute. It will return to the Bernard Sunley Lecture Theatre when, through the generosity of our present and hopefully future friends, we have been able to fund the repairs to our roof. Before we begin, we will have a few words from Brendan McCord, founder and chair of the Cosmos Institute.
Thank you, Professor Koralus. Thank you also to the Master of St. Catherine's College, Professor Bart von S. And thank you to the nearly 500 of you that signed up for this in the in-person and virtual formats. I'm Brendan McCord, founder and chair of Cosmos Institute. Epochal moments in science and technology have repeatedly transformed our understanding of ourselves. Copernicus dislodged us from the center of the cosmos. Darwin, whose artifacts are beneath us in this building, situated us within the animal kingdom. Einstein revealed the limits of our senses and our bare intuition. And each discovery forced us to reimagine our place in the universe. Each time, we emerged with a deeper insight into the human condition. Today, in the age of Turing, we face perhaps our most profound reckoning yet. What does it mean to be human in the midst of artificial intelligence? What does it mean to live a good human life when artificial minds can do what we do, and in some cases, much better? It is to address these questions that I founded the Cosmos Institute, to grow a community of thinkers and builders dedicated to human flourishing in the age of AI. And we're proud to support Professor Koralus as he launches the new HiLab, as he undertakes research that spans philosophy to code. To cultivate a new kind of technologist, we're establishing fellowships, fast grants, innovative educational offerings, including a seminar and Trinity term, that foster world-class AI expertise alongside deep philosophical inquiry. And today we're delighted to partner with St. Catz to bring one of the leading minds in the world at this intersection of human intelligence and computing, a Turing Laureate who exemplifies the very best of this new age, whose theory of educability sheds new light on learning, intelligence, and what it means to be human, and whose book you can claim with the QR code outside. We'll send you a follow-up email. Without further ado, I give you Professor Leslie Valiant to educate us all.
Thank you. Hello. Thank you very much for coming, and I'd like to thank Philipp for the more than generous introduction, and also to Brendan for sponsoring this event and the Institute. So I'll talk about a topic which I've worked on for a long time, maybe over 40 years, different aspects of it, but it's only recently that it's crystallized in a certain form, and this gave me the excuse for writing this book. Everything starts with Turing in this connection, so this is how I'll set up the question. So in some sense, he didn't solve everything for us, but he did ask a very fundamental question, which was, can every task done by humans be done by a machine? And people still ask this, and I'll just quote him for 3 sentences. This is a radio broadcast. So it is customary in a talk or article on this subject to offer a grain of comfort in the form of a statement that some particularly human characteristic could never be imitated by a machine. It might, for instance, be said that no machine could write good English, or that it could not be influenced by sex appeal or smoke a pipe. I cannot offer any such comfort, for I believe that no such bounds can be set. So the interesting thing about this statement is that it's not just a hunch of his, it's not just an opinion, but it is based on his central science, I call it Turing thesis, which is that anything which we can imagine being done mechanically by our brain can also be done by something you could capture mathematically, namely a Turing machine. And therefore, it follows from this very well-established thesis in science that this is a true fact. Ironically, of course, in fact, at every talk one gives on this subject, people do ask, what they say that humans can do which machines cannot. But so I think after 70 years, we should take Turing at his word. But this didn't solve everything, because what he didn't answer is, well, what is it that humans can do? So even if everything humans can do, machines can do, well, what can we do? And if we can't describe that, then what is all this good for? And the imitation game, the Turing test, there's some sense it goes in the other direction, that he gives an excuse for people not to ask the question of what humans do. Just saying that whatever machines, so he doesn't ask the question of specifying what humans can do. He says one should somehow avoid that. But I want to face that full on. So the question is, by the way, I think just to answer, to respond to Brendan's theme, so this idea that history of science is a sequence of insults to humanity's self-regard, Copernicus, Darwin. So I think the insult to human self-regard that we can be imitated by a machine should probably be dated to this statement of Turing. So I think this is kind of a historical assertion. Anyway, but we want to go a step further. So I claim that we don't really know what humans can do. We don't have a good characterization of what we do. So we certainly use the word intelligence to somehow self-characterize ourselves. And we do so in an extreme way. So we to measure our mental abilities, we say it's called an intelligence quotient. Maybe we emulate these by machine, we call it artificial intelligence. Some fear that intelligent machines will make us non-existent. And when we search the cosmos, we seek intelligent life. So you would think we'd know what intelligence is, but of course we don't. And when scientists famously try to pin it down, so board of the American Psychological Association gave a report, which was obviously caused by the fact that the IQ tests were controversial. And one statement from there is that when 24 prominent theorists were recently asked to define intelligence, they gave 24 somewhat different definitions. And of course, this isn't too surprising, because from the start, certainly from the start of intelligence IQ tests, I think Spearman may have originated that movement. The explanation, justification was always in terms of correlations. Okay, so people use IQ tests now. Maybe the result is correlated with how you do at university. But this kind of correlation business, maybe we should do better. So if we get people to do a test, we should at least define what we're testing. Just saying that you sit in there for an hour and what you'll do will correlate with something. Maybe we should do better than that. So what this book is about, educability, so it's a concept which is better defined than intelligence. I give a definition for it. I hope it's kind of more useful. It's not the same, but it's kind of a better defined notion of cognitive ability in a certain direction than we have, I think. So one question is, how do you get to, what question is this the answer to? So I think that's important. Okay. So the question which I asked was, what is the cognitive capability that enables humans to go from, this is the book publisher's illustrator's summary of the book. So the question is, how did we get from this arrowhead to a picture, that's a cursor on a screen, picture of. So what was the mental capability which enabled us to go from one to the other? And so clearly it wasn't a biological change. So if you want to talk about the last 5,000 years, clearly there was no biological change which spread through the whole human population. In fact, even if you look at the 300,000 years, the supposed age of our species, in fact, no one has found any mutation which has spread through the whole population which may account for this. So people have looked, but it's hard to find a biological explanation. So the more likely explanation is that we had some cognitive capability at the beginning, and this just keeps developing new behaviors and allows us to develop our civilizations. So to give it a definition, let's go to civilization enabler. So this is the capability we have which enabled us to develop our civilization. And so in some sense with this definition, I am also defining some things out to make the problem easier. So the many things which we share with other species, represented in the hall next door, we don't have to replicate. I just want to say I want to summarize what are our abilities which are in addition to what's common among other animal species. So vision, locomotion, emotions, these are everywhere in the animal kingdom. And so the methodology I bring to it is from computer science, and so I call it robust models of computation. So this is something I discuss at length in the book. It's a rather abstract notion. So the question is, how do we get some knowledge out of this kind of thinking? So I'm not doing experiments. I'm not doing questionnaires. I'm trying to find out something about humans without doing some stuff which other scientists do. And what this consists of very roughly is that I want to describe functions which are kind of well-defined mathematically. So a function is well-defined if you say what change you've made by executing it, what happened before, what's the situation before, what's the situation after. It's well-defined. And also, so any functionality you describe, you should imagine how it might be implemented in this universe. So it has to be computationally feasible, not something which takes infeasible amounts of computation. Okay. And so, of course, this general topic is the subject of many different academic fields. Okay, there are literally hundreds of different differences between humans and our nearest relatives, which scientists study. But I'm looking for kind of a very specialized one from that. And I'm looking for this civilization enabler, which is a cognitive capability, which enables humans to achieve the civilization we have. So, for example, so eyebrows, perhaps unique to humans. There's no theory why if you have eyebrows you can, make rockets go to the moon. Animal domestication, probably very important in our history, but again, no theory. It's not an explanation of how we can do everything we do in our civilization. There are many people who publish books about what's special about humans. So we're collaborative, we're social, we do social learning, and all important things for humans, also maybe for other species too. Intelligence, okay, not well defined. So symbols and language, so this gets closer, but again, if you just say language, language is important, clearly for humans it's very important, but just by saying language is not a cognitive capability. If you just teach a machine a language by itself, it won't do everything we do. So we need to round out this capability into something more. So what did Darwin have to say on this? Well, I think his basic position was that if you look through all the attributes you can summarize in one word or one phrase, like I have in the previous 2 lines, then he reckoned that humans are different from other species only to degree, not in absolute terms. So there's no one thing you can say in which we're absolutely unique. And I think probably that opinion, I think, holds. Basically, I think what we can do now, which he wasn't able to do, was that because we know a bit more about computation, we can express precisely more complex hypotheses. Okay, so instead of picking one word from the language, from the dictionary, and saying this is the secret, we're allowed to say something a bit more complicated. Okay, and by being able to say something a bit more complicated and still fairly precise, we can try to solve a problem which he couldn't. Okay, so we can try to contradict him. So this is kind of the program. So just one, since I know there are some philosophers here, so I think one of my favorite quotations is, so this is Gödel describing Turing's computability theory in very glowing terms. So Gödel said that Turing had succeeded for the first time in giving an absolute definition of an interesting epistemological notion, i.e. one not depending on the formalism chosen. So he had an absolute definition which somehow was more robust and didn't depend on exactly how you expressed it. Of course, now we know that Gödel was right because we have computers and all our computers are the same, and that's the notion of that it's you understand what a computer does independent of the particulars of your computer. So basically, I think what I've tried to do for a long time is to explore this same idea which Turing had, which is that by a mathematical definition which is robust enough, you can discover things about the universe which you can't by other means. You can't by doing experiments, for example. Okay, and that Turing succeeded with computation, and I think we can do this with other aspects of our cognition. So computation is just another human cognitive capability. People can compute, and we can do it for other things, I believe. And so the only thing which occurred to me actually when I made this slide, which I hadn't spotted before in this quotation, which I wonder what the philosophers think. So the interesting thing here is that, so what's this epistemological notion? So what was Gödel trying to distinguish computation from? Well, what Gödel was an expert on was reasoning, logic. He worked his life on logic. So I think he was saying, that for reasoning, although people had looked at that for thousands of years, no one has found such a robust notion of describing what reasoning is. Reasoning may be important and real and everything, but somehow it doesn't quite satisfy this condition. Okay, so so reasoning, in fact, isn't pure reasoning won't be one of the basic constituents of my notion for that reason. Okay, so this was my take on this quotation. Okay, so what I'll do, I'll just tell you what my definition is of educability, and then talk around it in some more detail, the various parts, and then give some consequences of this notion if you take it seriously. Okay, so what I propose is this notion of educability, it's a compound notion. You can't say it in one phrase. You can say it as the interaction of several parts. So we're familiar in physics. You've got Newton's laws. You've got 3 laws. Each one separately is very simple, but the interaction gets complicated. So I think that's the kind of analogy. So on one side, the definition is the following, that we have 3 basic capabilities, each of which I'll define in more detail. So the first one is we can acquire beliefs by generalizing from experience. So we have direct experience of things, and we draw abstract generalizations from it. So that's one. And for this, this will become exactly the standard machine learning paradigm, which we know well. So the theory of it and the fact that it corresponds to practical human phenomena is now self-evident, that you've got things like LLMs, which produce human-like phenomena. Okay. But of course, the point is that by itself, this isn't enough, so we need other elements. So the second element is a kind of reasoning, but it's a simple kind of reasoning where we just combine the various beliefs we have. This again is probably very, very basic, I think, in evolution. So if an animal has learned where to find food and then learned how to avoid something, then the animal can also chain together these various beliefs to decide on an action. So once you've learned various things about the world, you can also combine them, okay? And this is some sort of chaining, okay? And the third aspect, which maybe is the most uniquely human, is that we can also acquire beliefs by being taught, which means someone explicitly describes the step-by-step process of recognizing the truth of this belief. So sitting in a lecture room and learning about a formula in quantum mechanics, that's one example, or someone reading executing a cookery recipe, everything like that. We can take in an explicit description of something. Maybe this description could have been the result of someone else discovering it from experience. But, we don't have to experience the world, we just believe it, execute it. Okay. So these are the 3 aspects, but they all have to be in a rich enough domain to make it work in the real world. So they're integrated. So one is that we live in a fairly complicated world where we can distinguish objects and distinguish relations. I'll say more about this in a second. And also that we can do symbolic naming, that you can call your dog whatever you like, you can invent a name, and we're very adept at learning new words, new definitions, and relating it. People tell us fiction, character, we soak it all in. So we're very good at arbitrary names. So this is basically the setup. So obviously educability is meant to evoke education, and very roughly these 3 aspects are very close to very conventional ideas, of course, in educational philosophy. So number 3 is the conventional kind of lecture room kind of way of transmitting knowledge. Number 1 is more experiential learning, hands-on, and number 2 is applying what you know. So, for example, in mathematics education, so number 3 is learning about theorems. Number 1 is having examples of the concepts. If you have no examples, that's not very good. And number 2 is doing examples. Okay, so I don't have to speculate on some evolutionary timeline, but I may as well for a second. And the main point is that I think just generalizing from experience and chaining together what we've learned that way, these are very ancient. Probably every mammal or almost every animal needs to be able to do these things. But all this infrastructure at some point in the human line was further extended by the third one, which is that we can also take in explicit descriptions. something possibly abstract, someone else's experience. And so when this all came together, who knows, but I suspect, for example, it's possible that it happened in our, not in our species, but even before. But you know, I don't need to speculate, but I just have. Okay, so I'll quickly go through these three different things, and then go on to some consequences. So generalization from experience. So as I said, this is something which I'll interpret in exactly the same way we have in machine learning for a long time, both in theory and in practice. So this is very something we know a lot about. So conventional machine learning, learning by examples, means that you've got a learning algorithm. Deep learning is a currently popular algorithm, and you take examples maybe of pictures which are labeled elephant or not elephant, and you train your algorithm, and it comes up with a classifier, which is another little program. And then the property of the program, the classifier on the right-hand side, is that given a further picture, it'll tell you whether it's an elephant or not. Okay. So that's the general setup. And so both in theory and in practice, it's very important that this thing only works if somehow you ground this in some distribution D. So the examples have to come from somewhere. If you train your model in some world, and then you go to the other side of the world where everything is different, your classifier won't work. So the secret here is that you train in one world and you test in the same world. If the world changes too fast, this doesn't work. Okay, but so to formalize this, so I want to have more precise notions, and they have to be quantitative. And so this notion of this, how you formalize learning by example in a way which is quantitative. So this is probably approximately correct model, which roughly says that you do exactly as I said in the previous two slides, but also you impose a constraint on when you can declare success. Okay, and the criterion is that you can get more and more accuracy in classifying your future examples, maybe 1%, a tenth of a percent, 100th of a percent, but you have to make more and more effort. You're willing to make more and more effort. And the criterion is that the extra effort you have to make, so the effort is measured in computational steps. That's the simplest one, computational steps. But that usually also is proportional to energy usage, carbon dioxide emitted, etc. So it's a significant, and dollars, pounds, so it's a significant cost. As you increase the effort, the prediction error will go down fast enough that it's rewarding to do it. So with more and more effort, you can get better and better predictions, and affordably so. And the affordably so means this constant power decrease means that, for example, if by making 10 times more effort, we halve the error, then with making another 10 times more effort still, you want to halve the error again, and then do this repeatedly. Okay, so that's the kind of property you want. And so you can prove in theory that for significant classes of representations, you can learn this in the strong sense. And in practice, what's happening around us, the phenomena are exactly this, that these big AI companies, they're very, very tempted to spend 10 times as much money to train a bit better because they'll be rewarded. Then they're tempted to put even more money in. Okay, so this graph is a very important part of the current debate on AI. So that's the notion of packed learning. So just a comment about exactly what level of formality should you go, or precision. So this packed learning definition, you can make it a formal mathematical definition, but the important thing is that what it defines is just one thing, which is generalization. Okay, so just generalization. Now, when you talk informally about human capabilities, then humans are capable of many things, and people complain that these machines don't do what humans can do. So if you're familiar with machine learning, then there are a list of usual complaints, and they're valid. Okay, so humans, besides learning, can explain their decisions, etc., etc. And machines don't automatically do this. You have to do something extra to achieve this. Maybe you can't do these things at all. But they're worthwhile complaints. And in some sense, the reason why my definition of educability has 3 parts, and I don't stop at this first one, because this first one is clearly inadequate. Okay, so some people are so enthusiastic about current machine learning and think that it'll solve all problems. Well, so I don't think so. We need some other things, and so I'm trying to define these other things you have to add. So for example, let's talk about large language models. So they are trained to predict the next token, the next word segment, and in that you should believe they do that very well. That's science. But then, of course, people say, well, all these things I get from large language models, should I believe it? And there we don't know. Okay, so there's no reason you should believe what your large language model is telling you. We can't say, it's telling you to do this today. We can't say it's 30% accurate. We don't know. Okay, so current machine learning models are very good at exactly what they're trained on. If they're trained to recognize elephants, they're good at that. If they're trained to say the next syllable, they're very good at that and have nice, very smooth English. But beyond that, nothing is promised. Okay, so that's part 1 of my definition of educability. Okay, so my part 2 is a very basic form of reasoning, but I don't call it reasoning. It's just training. So the idea is that if you've what do we have here? Okay, so the idea is that if you've learned lots of things by experience, then maybe you think that it's going to be cold this evening, and you think when it's cold, you think you ought to take your coat, and you chain these things together, although each part is rather uncertain. So the phenomenon addressed here is that we are able to chain together beliefs which are uncertain. And they're uncertain because we've learned them, they're not axiomatic, we've learned them from experience, and they're not always true. Okay? So we need some angle on this. And so my angle, again, I've got a formalism called robust logic. And as always, the second part is you need something which is computationally feasible in some sense. You can't dream of something which you can't possibly realize with computation. But the main part is the notion of soundness, which is borrowed from logic. And soundness means that if you derive a conclusion by some mechanism, then if you derive it from things which you believe in, then your conclusion should be justified. Okay, so the main point of a reasoning mechanism is that from things you believe to be kind of true, you want some guarantee that what you deduce will be kind of true. And the kind of is at issue here. So what this will reduce to, this robust logic, is that so standard machine learning, we call it, this is a single learning box. So I like the analogy, the belief that the brain is just a big box which you train, input, output. So robust logic is still based on learning, but now you learn lots of small things, and maybe imagine that each maybe word in the English dictionary, you have a separate box for. You train and recognize for every word in the dictionary. And what the robust logic offers you is some principled mechanism in which if when you test this thing, if you apply this to a case and this thing fires and you say this thing is says it's going to be cold, then somehow you can feed this into another box which tells you what to do when it's cold. Okay, so it's basically that. So with standard pack learning, you've got guarantees for generalization, and if you do this robust logic, you've got the same, but in addition, you have some guarantees that when you chain together these different beliefs, then you'll have some reason to believe it. And naively, the statement is of the form that if you've got two rules, and you believe that they're kind of 99% rules, so if you've learned something from examples, then you can evaluate how much confidence you have in it. Okay, so if every time you go home in the evening, it's, you can go back to your training examples and see what percentage of evenings are cold. Okay, so you've got some faith in how accurate your rule is. So if you chain together rules which you know are 90% accurate because of your experience of them, then when you chain them together, you want some guarantee that it's still going to be more or less true. And maybe you've got 98% accuracy, so there's some degradation. But you want something. You want some explanation of why it's worth reasoning or training in a world where things are inaccurate. And so maybe a simplest way of explaining what this offers is that if I ask you, did Aristotle own a coffee-making machine? Most people think they know the answer. And so most language models kind of get this right now as well, although they didn't used to. But the interesting thing is that neither you nor the large language models were trained on examples which showed Greek philosophers with their domestic appliances. Okay, so we haven't seen any of those. Nevertheless, we can do this. And of course, we do this by some sort of training together different bits of knowledge we have. And so in machine learning, this is called out-of-distribution learning, that, so how is this possible? You're not trained on this. So the answer is that many out-of-distribution learning questions we do by reasoning. But you do need some system which explains to you why, if you chain together things you sort of believe in, then the conclusion you should also sort of believe in. Okay, so that's okay. So I also mentioned this thing that we need the world to be rich enough, multi-object world. So this is some crow doing some solving a fancy problem with a glass of water and putting stones in to retrieve a seed on a rising water level. And so somehow to describe what this crow is faced with, there's some complexity. So for example, there are many objects there. There's a seed, there's water, there's a glass. Water has a level. Then there are all these relationships. And so one has to somehow, the crow has to know about all this stuff. I mean, and somehow in a computer we do have to represent it somehow. And in our system, it has to be rich enough to cope with this kind of description. Okay. So just to say slightly more detail. So the idea is that in this robust logic, it's a system. One feature of it is what I call a mind's eye, which corresponds very much to working memory for psychologists. So this idea of what you're conscious of at any moment when you're trying to work out what you're doing. And so at any moment here, there may be two tokens, and one of them in your mind's eye is a dog. And you also know that the other object, which you don't know yet, is liked by the dog. So these are the descriptions you can have in this robust logic. And the idea is that you'll figure out that this thing which the dog likes is a bone. So how do you do that? Well, in robust logic, a rule is not like a logical rule, but it's a classifier. So it's like having learned a way of recognizing when something is a bone. So as in my earlier picture, suppose you have, for each word in the English language, you have a separate box which trains to just say, is this an elephant, is this a bone? So in robust logic, you have that. And so if in a description of the world like this, you go through your rules and see which classifier is satisfied and will help you to complete the picture. Okay, so in robust logic, this is what you have. There's also one difference between this kind of logic and More standard logic is that maybe here you expect an implication sign, but here everything comes from machine learning in my previous sense, which is always a kind of an equivalence or approximate equivalence. So when you train a classifier to recognize elephants, you recognize elephants or also non-elephants. So both sides are important. But these things, these equivalences, you can also chain just like implications. Okay, so basically, you represent situations in your mind's eye, and then these learned rules get chained, and that's how you draw conclusions, plan your day, and things like that. Okay. And also, all the training is done in things in your mind's eye. So the training examples are just the things which have come through your mind. So all your knowledge is, the real world doesn't quite exist for you. You're trained on what you perceive of the world in this system. Okay, so there are some theorems which describe what I've said. Okay, so that's the end of chapter 2 here. Back to the main course, which is describing this civilization enabler. So these two aspects of learning by example, training, I believe, are very ancient in evolution. And now I'm going to add the third part, which is, I think, very much rarer, which humans do mostly. So we also allowed this architecture, which I've described up to now. We need everything we've described. But in addition, instead of taking a rule just by seeing examples, it can take a rule for describing elephants by programming it, someone telling it. This is the rule for predicting an elephant. And then if someone gives it a rule, then basically what you're doing is to interpret the rule step by step. And then this just becomes the universal Turing machine. The idea is that we were capable of being told procedures and understanding how to follow them step by step. So we are universal Turing machines in a very memory-limited way. If someone gives us a very long procedure, maybe on paper, we can step by step follow it. Okay, so this is important. So I claim that these three capabilities, this one together with the previous ones, is what educability is. And okay, and so maybe just last word on this, on the instruction stuff. So clearly the upside of being able to take instruction is the obvious one that, well, it allows discoveries maybe with painful and costly experience to be shared. So a classroom of people can hear about the results of quantum mechanics without everyone having to repeat all the experiments. So it's extremely efficient in spreading information, which is very hard to obtain in the first place. And some of these information which is shared can be very fundamental, like ways of reasoning. So something like how to do arithmetic, must have been very difficult to discover. Someone did, but we all learned arithmetic in primary school, and it's very good for us because it's an extremely efficient way of sharing something which was clearly very difficult to discover. So clearly, this is how science can accumulate complex cultures, etc. Okay, so this is basically the proposal, and so each tree part is something which is somehow you can wrap your mind around, something simple in itself, but I think it's the interaction which produces sort of rich set of phenomena. So if you want just a picture illustration, then this is the following: that we live in a very complex environment, and so does every animal which lives in the bottom of the ocean. And so pack learning, robust logic, these things are all to do with fitting yourself to your environment, to being able to predict your environment and survive in your environment. Okay, so somehow they're very safe. But this third edition that I just put in my brain something you've told me, that's something totally new. And it's very risky, because who knows, maybe what you've told me is nothing to do with reality, nothing to do with my interests, nothing to do with anything, maybe something to do with your interests. So it's a very risky, novel addition, okay? And, okay. So that's the pictorial thing. So now I want to say very briefly about 7 different thoughts you could have after this, okay? And the first thought is that being educable as a species may have a serious downside. And this downside is what the last picture illustrated, is that before we have this ability to just be told things by other people, our behaviors are very grounded in real experience and somehow, very safe. But it seems that we have this incredible ability to absorb instruction from others. As an addition, we've got incredible, so this educability is a very powerful way in which we can absorb information from the world. But I've nowhere mentioned any ability to check whether the information is true, okay? There's no way of verifying, certainly, a general rule which someone has just told you. So this seems that maybe we're thrown into some sort of disequilibrium. We've got these great powers, we can listen to each other and believe what each other says, but we know it's very hard to tell whether what we're telling each other is true. So it seems that we're kind of rather easy victims of arbitrary belief systems, ideologies, conspiracy theories. There's nothing new. And so maybe the one emphasis I want to put, so besides just complaining that we're subject to all these bad things, is that I think we should acknowledge more that this is somehow a weakness in ourselves. So it's a question of self-education. So there's been propaganda always, and we've always been easily fooled. Okay. Okay, so I'm saying that's a downside of being educable. Okay, so let's go on to the other things. Okay, so people say, well, great, educability, how do I improve my educability? Answer is, I don't know. But if you want to discuss this, then you'd have to be able to measure it. Okay, so if you want to say, I can improve my educability, or the population can improve its educability, then you need some measure of it. So what would a test of educability look like? And that's an easy question. So it will test only for knowledge acquired after the beginning of the test. So you walk into a test, maybe a 1-hour test, and the thing isn't to test you on your previous knowledge, it's not to test you on any previous trait or ability, except for this educability thing. Okay, so the idea would be that you walk in, you'll be given some information, and you'll be tested on how well you can apply the 3 different things I have. Can you generalize well? Can you apply the generalizations you obtained? And also how much, if you're told information, how much you can chain it together and put it all together. So I think the aspiration of this kind of test is a new kind of aspiration. I don't think of the millions of tests around, I don't think anyone, okay. So some of the questions may be similar, but still, most questions on standard IQ tests wouldn't be right. So for example, if you say, apple is to seed then, some typical question, this is no good for us because I'm testing you on your previous understanding of some relationships. I haven't told you anything new. Okay, so in the educability test, I have to try to educate you. I tell you something new and see what you do with it. Okay, so it's a different aspiration. Okay, so number 3. So this is the issue of on the one hand, one likes mathematical models which are clean. On the other hand, there's the other side is that this model has many parameters. But other models also have parameters. So, for example, machine learning, standard machine learning, is very pure in some sense, but it's got some parameters. You have to choose your learning algorithm. But also, as we know, the training set, data set is very important. The behavior of the trained system depends entirely on the data it's trained on. So it's, it's a very enormously parameter form. So, so educability will have many, many more parameters. So it's not as elegant as some of the other things are, but I still think it's got meaning, okay? And so, for example, this mind's eye I described, it needs some management operations, like how often do you refresh it? You know, how often, when something new happens, how ready are you to forget about what you've been thinking about? Okay, so it needs some of those. A very important thing is what I call belief choice. So if you've got any standalone system, maybe even a standard machine learning one, you know, how does it know whom to believe? Does it believe everything it sees? Okay, so even if you're a standard machine learning system, do you train on every example you see? Probably you shouldn't, okay, because, and certainly there's a lot of psychological literature that humans have, you know, fairly numerous kinds of strategies for choosing whom to believe, you know, authority figures, parents, whatever, okay? So that's a parameter. How you form compound concepts, that's also important, that you can have as targets of your learning, say, conjunctions of two concepts you know, how do you choose them? So this is important for, I suppose, creativity. You form some new concept, you know, gravitational attraction, and etc. Okay, so that's another parameter. And so what I call teaching to reason. So my reasoning is a very basic training mechanism, and I think then different kinds of reasoning, I mean, some may be innate, but some will be taught. So arithmetic is clearly taught, probability theory is taught, so estimation of probabilities doesn't come that naturally to people, causality. So I think of reasoning as being composed of different methods of reasoning, many of which are taught, and you know, if you build a machine, you have to choose which to teach. And in fact, if you design an education system, you also have to choose the same things. So I think this educability, having many parameters, is also just a restatement of the fact that it's very difficult to design the best education system in the world. And all the problems you have in designing an education system, you will have the same problems in designing a machine, because you've got the same choices. You know, you can't do everything. You have to choose which choices to make. So when you want to make a machine which absorbs information from the world, you have exactly the same choices as in designing, as being an educator, I think. Okay, so okay, so I'm saying parameters are not a bug of the model, but a feature. Okay. Okay, so briefly, people talk about singularity. So one argument, R.J. Good, was that an ultra-intelligent machine is something which will surpass all the capabilities of any man, however clever, and then conclude that at some point machines will take over our lives. So I'm a bit skeptical about this particular fear, because so one reason is that, you know, it's hard to define what this one dimension of superintelligence is going to be, so no one can define that. And so what if all our capabilities and the capabilities of machines can be expressed in terms of explicit, prosaic, understandable components? So the components I've described are very concrete, understandable, prosaic. And what if that's all there is to it? So we'll have machines which can do these various things. We have to decide, you know, how to train them. We have lots of decisions to make, but nothing is kind of mysterious. Okay. So what if this is all there is? Then maybe there's less to fear because we kind of understand what we're doing. It's complicated, and we know that, you know, humans are complicated. Educating humans are complicated. We're just inheriting the same thing with machines. But there's nothing, you know, inherently mysterious, magical to fear. Okay. Okay, so getting to more controversial things maybe. Studying human behavior. So it seems that in studying human behavior, it's difficult to do because results are difficult to transfer in time and space. Social science theories come in different flavors. What does that mean? There were the eugenicists who believed their science wasn't right, although in fact many of the practitioners were the best statisticians ever, and in fact the social sciences still use their statistics now. Okay, so there are lots to explain. So the only thing I have to add is the idea that the word educability gives a name to this problem. Okay, so I'm saying that among particles, mice, biological cells, humans, the humans are the ones which are most easily change at the least opportunity. Okay, so the least change in environment will totally change their behavior. So if you want to make a science of behavior of any of these, humans are by far the most difficult because they change so easily in all these different ways. Okay, so educability gives a word for the difficulty, I think. Okay. Education, well, so if you believe this theory, then education should be humanity's central preoccupation. Okay, it would be nice to contribute to some sort of more scientific basis for education. I think education in universities has a lower status than it should have, and we should do something. Okay, and then lastly, this educability proposal is described in computational terms, so it is a technological proposal, as well as being a theory about humans. Okay, so you can interpret it either way. And so the book is not technical, but if you go through the notes and appendices, then you can dig out some technical recommendations there. Okay, so thank you. I'll finish there.
Thank you, Les, for a really exciting lecture. So we now have about 25 minutes for questions from the audience. And Les will basically pick his own questions. Okay. And then Theodore and I will be running up and down the aisle on both sides to get a microphone to you, which means it's quite important that you keep your hand up if you do want to ask a question. But I will treat myself to the first warm-up question. So what if somebody said, okay, well, only this morning was I running my essay through Claude to make it sort of sound more like a distinction level essay. Well, it didn't know that content before the, as it were, test, right? Because I had to tell it about my essay. It then did something with it that was, broadly speaking, useful and intelligent seeming. Why would that not be just a case of, here we have a system that's educable because it can be, as it were, taught after learning, here's the essay, and then do something with it?
So my impression is that what you're really asking your LLM is to exploit its previous knowledge about something, make nicer sentences, add some case you haven't thought of. So I think my interpretation is that you're really using LLMs as a mechanism for looking up knowledge and putting it in very nice English.
Thanks for the talk. In your one of your conclusions, you said that maybe we can test for educability. I wonder if you think that implies that some humans are more educable than others, and if you're worried about things like eugenics and tests of intelligence and risks that come from operationalizing these things. Do you think that I guess two questions. One, do you think that people who are more educable than others are more human? And yeah, have you thought about risks of operationalizing humanity?
Yeah, okay, so great set of questions there. I suppose, okay, so one aspect is that if one thinks that educability is a valuable ability, and it would be valuable, say, for the human population to increase its educability, then somehow we should understand it more. So personally, I've got no view on the experiments have to be done. So it's possible. So one question. So maybe it may be that educability is a totally everyone's got their own educability and it can't be changed. Okay. I mean, I doubt that almost every human capability can be changed by some sort of training or some sort of intervention. So I think finding out what intervention helps educability would be helpful. Okay. So it's one question: is it a worthwhile thing to try? Okay. Now the other side of the question: what are the dangers? So I agree. So I think the last thing I want is to give people privileges according to their educability. So the way I try to phrase it in the book to avoid these questions is to say that educability tests should be used to with the aim of increasing the educability of a general population. It should be used against an individual. And certainly and the one important thing about this is that, so tests are used in schools to test children who identify whether they've got special needs. And so these tests aren't abused in the sense that people don't train for them. Okay, so the last thing I want is people to train for these things. So if somehow one could have educability tests which people don't train for because there's no individual benefit to it, then one could somehow use them to do science to understand ourselves better. But it's a very important issue, yes. Thanks for raising it.
Thank you. So the third Turing thesis says that any computation that can be done by a human can be replicated by a machine. If humans are evolving over time, do you think the machines should also evolve over time to match the human?
Well, I think the Turing thesis kind of says that if whatever, say a particular human can do now, in principle, you could program a machine to do that, or you could train a machine to do that. Okay, so if the humans have changed, then probably the programming of the machine will change. The education of the machine will have to change, but I imagine it would still be the same overall structure of this educability. Okay, so.
Hi. Near the beginning of your talk, you mentioned Turing not answering the question that you were going to tell us about, which is, what tasks can humans do? I just wonder if you could expand on that a bit, particularly putting it the other way around. What are the tasks that you think humans can't do, and is there some general description of what that class is?
Well, I think so I believe humans, in the main, in this domain I'm looking at of these cognitive skills, can do these kind of things. There are lots of parameters in this. We've got strong limitations of these parameters, how much memory we have, and everything else. So there's a lot of computational limitations. So I have a very simple answer to this, which people have studied, I think, in this room. So even with basic machine learning, fact learning, certain things you can do. There's a lot of evidence that certain kind of functions you cannot learn. And for example, functions to do with encryption. So by looking at the behavior of some encryption device, you still can't figure out how to encrypt further messages. So in this way of looking at the world, the things humans or machines can't do are those which just take too much computational resources. But it's a complicated question you've asked, so I gave you a quick answer.
All right. It works. Okay. So first of all, thank you for a very interesting lecture, and sorry for maybe a little bit ridiculous question.
Okay.
So I think that educability might be actually be abstracted away by learning from experience. Because
sorry?
The educability could be abstracted away as a component of learning from experience. So
sorry, that's the last phrase, as a
component, a part.
Part, okay.
A part,
okay.
a subset.
Okay.
So even if there was a single agent, like a person, and nobody could educate it, we have something like our past selves. And memory could be seen as a text that is constantly being read. And as we all know, if we have a text, then the meaning depends on the reader and their experiences. So our future reading is different from our current reading. So we could say that our past selves are actually educating us. And we could see our past selves as another agent that is educating us in not really our experience, but our actually past experience. So generally, my question is, is there any difference actually between educability from like entirely foreign agent and our past selves if we need to reinterpret our past memories anyway? So we can forget things, we can stop trusting our past experiences, and is this any different?
Well, I think one difference is the quantitative one, is that by learning from other people, you can learn lots of information which you don't already know. Educability is a very efficient way of pooling together knowledge from very many people individually doing different things. So that's one answer. Okay.
Maybe as a quick follow-up to that, I mean, another way of taking the question would be to ask, okay, do we think of what's coming in from other people as sort of categorically different from, let's call them the formulas that we have on board in our kind of in our own knowledge base, right? Or do we want to treat that as just sort of directly entering into the general cognitive economy, then to be treated in largely the same way in which what we already have on board is treated?
So yes and no. So in one sense, it's the same because the formula you treat it the same. But in other sense, it's different because for various reasons, you have to be a bit suspicious of what's coming in from outside. That everything you know, you have to ascribe some level of is this part of your current belief system or is this not? So for example, one issue may be that we can probably keep several political theories in our heads without committing to any one of them. Okay, so there's some beliefs we actually believe in and we act out, but also we have the capability of manipulating beliefs without actually being committed.
Hi, thank you for the talk. I'm curious about your level of optimism with respect to belief choice, in particular our ability to improve in belief choice. And to draw a comparison to, say, scientific theorizing, it seems like we have a more monotonic increase of increasingly sophisticated theories. Do you think that choice of the correct belief set happens in the same way, or are there reasons why it seems harder to accrue more sophisticated belief sets through history? I really don't know whether there's a good solution to belief choice. So if you mean in the course of human affairs, obviously we're choosing sources of information which we trust. Having source of information which everyone trusts, that's a very useful device. But if all the time we have to make very subtle decisions about who to believe, then I think I don't see how to be optimistic about being able to do that. Okay.
Hello. I was wondering. So you said, or you motivated this notion of educability a lot by learning, also from learning knowledge that others communicate to us, also for reasons of efficiency and space, memory space. And a lot of it is about collaboration, that somebody teaches us, that somebody gives us examples that are helpful for our learning curve and so on. But then the mere definition and what you answered to the question about testing for educability is more about a property of an individual. So I was wondering, how would you define, or do you think there's a way to define a concept of educability for a group or a community? Would you see any potential in this? Would it? Yeah.
Yeah. So you're right. So what I'm describing here is certainly an individual capability, but as you say, it draws much of its strength from the fact that it operates in a community. Yeah. So that would be a good direction to go in, I think. I don't have any good definition for. I haven't got any good thoughts, but people do ask about that, and I think that's a very, very valid question.
Yeah, I think somehow this justification of the educability lies in this not being so much with the focus on the individual person. That's also why we have to be careful to test for this, just to evaluate humans more than the effect on a community.
Right,
yeah.
right. Okay, so, okay.
So this sort of question brings me in the direction of what I was wondering, because basically number 3 on your list sort of brings in this group, so everybody else becomes important. So and you had these downsides of educability, that you can sort of learn conspiracy theories and so on. And I guess what I'm wondering if one can compare things from computer experiments to social situations, because we have these examples where say a sect is forming. Lots of people believe, are re-educated basically by somebody, and then you go and commit suicide the whole group or something like that. These things seems to be about the negative side of educability, and I'm just curious if one can get the same kinds of situations if you simulate like a number of these SLBs, the learning boxes, and set up a network, and can one poison them in some way to explore this phenomenon, or learn about it? I suspect I suppose it's only too easy to have a system go and believe nonsense. I think it's just too easy, and how to guard against it isn't so clear. So I think it's I do think it's a fundamental weakness we have, and I don't know of any obvious cure. But so you're asking whether experiments on machines may be useful? Possibly, yes.
Hi, I'm just really curious about your views on AI deception, because oftentimes the large language models do be flattering to our opinions, and maybe and researchers in AI categorize that as the large language models being deceptive. And I was really wondering, what do you think of it? Maybe is machine learning being more showing the educability, the capabilities that you have mentioned? I don't know whether I understand this concept correctly, but I'm really just curious about your views on how, like, the large language models being really maybe more human. So actually I can't see you. Can you put your? Oh, sorry. Okay. So our language model is more human in the sense that they can do what? So I just missed the beginning of your question. Yeah, because the GTP or the large language models are being deceptive. You say like, maybe you ask the GTP to introduce you whether their opinion to like a political party, and you said I like A, and it will be flattering to your opinion that like A is more better than B, which is the answer it may initially gives. So I'm wondering, that is a sign of educating capability? Of the LLMs having an educating capability?
Yeah, so I haven't discussed the capability of educating. I've discussed the other side of someone being educated without describing kind of what the agent who is doing the education without characterizing them at all. So I'm not sure whether I understand your question. So I think we have whatever our mental capabilities are. I think we're very ready to be educated. We're ready to listen. And so probably we listen to LLMs using whatever our biases are, way of listening. So I wouldn't like to attribute anything to the LLM here. I think we're studying ourselves, our behavior and how we respond to LLMs.
Thank you. I'm curious about what, if anything, educability might be able to tell us about the notion of ethical AI. So I was wondering how you describe the relationship between educability and, however you want to define something like ethical AI.
Well, yeah, there may be no relationship. Because I'm describing kind of like a capability, computational capability, and I don't think it's directly. I don't think they're related. No. Okay.
Hello. Thank you for your thank you for your talk. I am kind of stuck on your evolutionary timeline, which I know you only sketched. So, but I was wondering if the first two parts of your educatability have evolved so much before humans, a lot of people might have the inclination to say, well, it's specifically part 3, that the explicit teaching is what enables civilization and makes it possible. I guess this is the same people who would say that it is language which makes us humans. And I was wondering sort of what your model for the civilization enabler sort of really gains over just this specific part 3. And I guess more specifically, I say that in the sense that, is it even possible to have part 3 without 1 and 2, and then to say that part 3 alone is not enough? Because for me, it's sort of, I can't help but view it almost as a sort of progression rather than separate necessities.
Yeah, I mean, that's a reasonable question. So 3 alone technically is basically Turing computability. And so one could ask, I mean, so in fact, at one point in my book, I did have a chapter on this, but someone said, who would ever ask this? But you have. So I think just saying that we can simulate procedures we are told, isn't that doesn't account for much of our behaviors, right? Because we also have to discover things about the world. And okay, so the point of having the 3 things together is that you need a joint capability which together has some richness and explains our behavior. Okay, so just any one of them by themselves, I don't think is a rich enough capability to describe it. But in some sense, I mean, it's possible that what you're saying has some technical truth, that in terms of evolution, it's possible that at some point we became universal Turing machines in some simple sense. And yeah, so I understand your question, but I was trying to describe a capability which is really a capability which, for example, you can aspire machines to be able to do, and then they're useful. Yeah.
So I have a slightly more practical question. Over-information theory is basically, if you inundate humans with too much information, they can't analyze it, they use heuristics, and they become emotionally driven. So there's that risk factor with Gen AI today. You put so much information out there, people are going to get emotionally driven. It's happening everywhere, and it's weakening scientific inquiry. The second component of it is, as humans, we tend to kind of overestimate delivery of scientific progress in the short term and underestimate in the long term. So maybe 2 years from now, ChatGPT won't be, a new version of Plato or the next Newton, but maybe in 25 years it will be. The average person that's doing a remote work job honestly is contested by the capabilities of ChatGPT today when it comes to organization, taking notes, things of that nature. And the concept of re-educating that person to go from basic analysis to learning stochastic calculus while they have kids at home seems like a big challenge. And so the garden variety answer from Google and other companies is, oh, we're just going to re-educate the workforce. But practically speaking, and maybe on a 20-year span, what is it that can be done to kind of involve our institutions or more for our education if it's really, as you were emphasizing, the primary thing that we should be concerning ourselves with? What would you do in order to make sure that we're prepared?
Well, the only aspect to which I can, which is relevant to which I can speak, is that we should understand ourselves better. So have a more scientific basis for understanding education. So the only thing which may come out of this, which may address your concerns, is that, for example, we could find out better ways of educating people and understand the limits of it, what was possible and what was not possible. So it's so just understanding ourselves better. So this is one angle to understanding ourselves better, and I think that's important in all kinds of domains. Okay.
Sorry. Yeah. Thank you so much for the talk. I have 2 questions. The first one is: do you see educability as a one-directional activity? Does the educated agent convey feedback to the educating entity?
Well, so in this model, I'm just looking at the capability at each agent being the recipient of information and how well this agent does with it. Yeah, I mean, you could try to have models which are more complicated, and with feedback, I haven't gone there.
Thank you. And does this model enable creativity?
Does it enable creativity?
Does it assume that creativity exists?
Well, yeah, I mean, it acknowledges it in some sense, that so you have some, as I mentioned, in these management rules you have to decide on. I mean, the issue I do look at is to what extent you can form new combinations of concepts which you already know. So the idea being that even the most creative scientists usually, either subdivide a concept or they combine concepts, and of course some of these things are the good ones it's very difficult to make. So in designing these things, you have to make choices of what to do. So it does address the problem. Okay.
We'll have one last question.
Hi, thank you so much for the really interesting talk. So in anthropology, there's this concept called ratcheting, where learning from one generation is able to be passed on intergenerationally. And this is something that specifically sets us apart from primates, for example, who are able to learn within generations and can learn how to use tools and teach this to other primates. But they don't seem to be able to pass this information on between generations. Is there a place for ratcheting within your concept of educability?
So is there room for...
ratcheting.
For?
Ratcheting.
Ratcheting. Well, yeah, I mean, okay, so I don't exactly know in what sense you're using it. But I mean, I stand with what I said, that these mechanisms I have are ways of transferring information, and the only mechanisms I have are the ones I described. So I'm not sure whether they satisfy your criteria.
Please join me in thanking Les for an excellent show. Yes, and by no means thank me, but if you're interested in the themes that we discussed today, so there will now be an annual lecture of this type, and stay tuned for more announcements about opportunities related to this kind of sphere of concepts. So thanks very much.
quite difficult.